Have you ever looked up at the night sky and wondered how far away everything really is? From Earth, the Moon, Mars, and distant stars all seem like neighbors, but that's just an illusion. The distances between these objects are unimaginably vast, and learning to measure them is one of humanity's greatest achievements. For centuries, the sky looked flat, a beautiful picture with no sense of depth. Unlocking the third dimension, distance, changed everything. Each measurement became a rung on a cosmic distance ladder, revealing a universe far larger than anyone imagined. This is the story of how we measured the heavens, transforming our wonder into knowledge and finding our true place in the cosmos. Let's start close to home, with our nearest celestial neighbor, the Moon. It's a familiar sight hanging in our night sky, but how well do we truly know it? How do we know it's approximately 384,400 kilometers away? What methods do scientists employ to ascertain such precise measurements across the vast emptiness of space? The answer lies in a technique called radar ranging. It's a cornerstone of modern astronomy. Scientists fire powerful bursts of radio waves, a form of electromagnetic radiation, at the Moon. These waves travel at the speed of light, then they meticulously time how long the echo, the reflected radio signal, takes to return to Earth. Knowing the constant speed of light and the precise time it takes for the signal to make its round trip, we can calculate the distance with incredible accuracy. The precision is astounding. This method isn't limited to just the Moon. It works effectively for nearby planets too, Venus, Mars, even asteroids, giving us a reliable and consistent tape measure for our entire solar system. It allows us to map the positions and movements of celestial bodies with confidence. Furthermore, radar mapping has revealed hidden surfaces, things we couldn't see with ordinary telescopes. A prime example is Venus's perpetually shrouded terrain, hidden beneath its thick, opaque cloud cover. This technology has also helped us plan complex missions across the solar system, ensuring accurate navigation and trajectory calculations. These fundamental measurements are the very foundation upon which we build our cosmic distance ladder, allowing us to probe deeper into the universe. With radar, we transform what appear to be wandering points of light into a precisely mapped physical space, giving us context and understanding. It's absolutely essential for both understanding and safely exploring our solar neighborhood, paving the way for future discoveries. Without this crucial tool, we'd be adrift, lost in the vast, incomprehensible dark. When it comes to measuring the vast distances to stars, traditional methods like radar simply won't cut it. They're far too distant for radar signals to bounce back in any meaningful way. The sheer scale of space demands more ingenious techniques. Instead, we rely on a clever trick of perspective known as parallax. This method allows us to indirectly measure the distance to these celestial objects by observing their apparent shift against a distant background. To understand parallax, try this simple demonstration. Hold your thumb out at arm's length and switch viewing from one eye to the other. You'll notice that it appears to jump against the background. This apparent shift is parallax in action. The closer your thumb, the more pronounced the shift. Astronomers leverage this same principle, but on a cosmic scale. They use Earth's orbit around the Sun as a giant baseline, effectively creating two observation points, separated by millions of kilometers, to do the same with stars. By meticulously photographing a star at 2 points in Earth's orbit, typically 6 months apart, when Earth is on opposite sides of the Sun, we can observe a tiny shift in the star's apparent position against the backdrop of much more distant stars. This shift defines the parallax angle. Now, keep in mind that even for the closest stars, this shift is incredibly minuscule, often smaller than the width of a human hair seen from a kilometer away. Therefore, measuring parallax requires extremely precise telescopes and instruments, but with these advanced tools, we can measure it accurately. Once we have the parallax angle, we can use simple trigonometry, a branch of mathematics dealing with the relationships between the sides and angles of triangles, to calculate the distance to the star. The relationship is straightforward. The smaller the parallax angle, the farther away the star is located from us. Parallax was a groundbreaking technique, as it gave us our first direct and reliable measurements to other stars beyond our solar system, allowing us to determine the distances to stars like Proxima Centauri, the closest star to our Sun, which is over 4 light-years away. Because of its accuracy and reliability, parallax is considered the gold standard for mapping our stellar neighborhood, providing a fundamental framework for understanding the structure and scale of our galaxy. In the grand scheme of things, parallax serves as a crucial rung on our cosmic distance ladder, a sequence of methods used to determine the distances to increasingly remote objects in the universe. Telescopes are our windows to the universe, collecting faint light from distant objects. The bigger the telescope, the more light it gathers, letting us see fainter, farther objects. For parallax, telescopes must detect tiny shifts in star positions, impossible without their precision. Space telescopes above Earth's atmosphere see with unmatched clarity, measuring even smaller angles. But telescopes do more. They help us find standard candles, stars with known brightness. By comparing a standard candle's true brightness to how dim it appears, we calculate its distance. This lets us measure distances to other galaxies, extending our cosmic map millions of light years. Telescopes are not just viewers, they're our primary tools for decoding the scale of the cosmos. Another way we measure distances in the solar system is by sending spacecraft and tracking their journey. As probes travel, they send signals back to Earth. By timing these signals, we know their exact distance. Analyzing the Doppler shift in the signal reveals their speed with astonishing precision. Tracking spacecraft like Juno or Cassini lets us map planetary gravity fields and refine our models of the solar system. These measurements are vital for planning future missions and understanding planetary interiors. Our robotic explorers don't just take pictures, they chart the territory, making the unknown familiar. They're the scouts, paving the way for all who follow. Spectrometry doesn't measure distance directly, but it reveals a star's properties, letting us infer how far away it is. By splitting starlight into a spectrum, we see unique patterns, cosmic barcodes, telling us a star's temperature and type. The Hertzsprung-Russell diagram links a star's type to its true brightness. By comparing a star's true and apparent brightness, we estimate its distance, a method called spectroscopic parallax. This technique works for thousands of stars far beyond the reach of geometric parallax. It helps us map the structure of our galaxy, revealing spiral arms and star clusters. All this information is encoded in ancient starlight, decoded by our instruments. Spectrometry turns light into a map of the cosmos. Now, when we look up at the inky canvas above on a clear night, we see a universe of almost unimaginable depth and scale. A cosmic ocean stretching out in every direction, filled with wonders beyond our current comprehension. It's a neighborhood of neighbors both near and far, each star a sun, each planet a potential world. Each measurement we take, each data point we collect, from the faintest radar echoes bouncing back across light years, to the subtle shifts of parallax and the analysis of starlight's ancient journey, reveals the true, breathtaking architecture of our cosmic home, the Milky Way and beyond. Knowing these distances, understanding the vast gulfs of space, transforms planets and stars from distant myths and legends into real, tangible, and potentially reachable worlds. It grounds us here on Earth, showing both the almost incomprehensible vastness and the underlying unity of the universe. With every new mission launched into the void and every new telescope peering into the depths, we push our map further and further, expanding our knowledge, reaching out to galaxies billions of light years away, glimpsing the universe in its infancy. But it all starts right here at home, by carefully measuring and understanding our closest neighbors in the solar system and beyond. In understanding these distances, the scale of our local cosmic environment, we begin to truly find our place in the grand tapestry of the cosmos, our significance and our insignificance. And the universe, once a cold and alien place, becomes a little less lonely, a little more familiar. The night skies